Today we'll continue looking at hypothesis testing. In particular, we're going to continue to look at some details in our null hypothesis statistical testing. In the previous video, we looked at the Salk vaccine trial. And we created that null sampling distribution. And then we looked at what is the probability that Salk got this difference in polio infection rates between vaccinated and unvaccinated kids under that null distribution. So what's the probability that we would get that by chance alone? And we only looked at the probability on the right-hand side, only at that result or larger. And so that really was a one-tailed approach. Most of the time we're not going to be doing one-tails. We are going to be doing two-tailed tests. In other words, we're going to accept probability values that could occur on either side of that null distribution. And that's called a two-tailed approach. One of the things we have to do is choose a significance level, and we've been talking about this a little bit because we've been saying we're operating under this rare event rule. And what we want to know is if we get some probability value under our null distribution, what constitutes rare? And so we get to set this. We get to decide what we consider rare event. And that's what we call setting our alpha level. And when we set our alpha level, we're saying that if we get a p-value that is below it, we're going to reject our null. If we get one that's above it, we're going to fail to reject our null. And here you can see some null sampling distributions where we can set our alpha. Here's the sweet spot right in the middle. And we're going to set our alpha at 0.05. Just like we did for getting a t value in order to create our 95% confidence intervals. So we're going to be at a probability value below 0.05, at which we call that rare, and thus reject our null. And if it's above it, we'll call that not rare, and then we will fail to reject our null. And again, that 0.05 probability is going to be split between the right and the left tail. So we're going to have 0.025 in the right and 0.025 in the left. Now, I don't have to set it that it's a standard thing in null hypothesis testing, but you could set it very, very low. I can't even see it under that curve there on the left, or very, very high. At very, very low, it will be hard to get p-values that low, and we're going to see as we move forward that the power to be able to detect that is going to be low in many cases under normal circumstances. In the other circumstances where the alpha is very high, we might easily be able to detect probability values above or below 0.75. But if it's below 0.75, so we got a probability of 0.6, is that meaningful enough? Is that a rare event? Would I say that couldn't have occurred by chance alone? Probably not. So we set our alpha level, but what we have to realize is that that's an error rate. Okay, we could be wrong. We've talked about that all along. We could be wrong. So when we set our alpha value, that's called our type 1 error. So it's saying we could reject the null when it's really true, and that's called type 1 error. Type 1 error, otherwise known as alpha error rate. Okay. Now, there's another type of error that we haven't seen, and that's retaining the null when it's really false, and that's called type 2 error or beta error. So this is a handy chart you really should highlight in your notes. So in this, we're seeing two things. We're seeing the truth, as if we knew it, right? Here's the reality. The truth is out there. Then we have over on the left column conclusion. In other words, we sampled a population, we did some null hypothesis statistical testing, and we either rejected our null or we failed to reject our null or retained our null. Okay, let's say we rejected our null. That was our conclusion. We got a low p-value below our alpha. And so if we rejected our null, we could be wrong, and that is our alpha error rate, because the null in reality could be true. Okay. We could also be correct. And if we're correct, that represents the power, and power means the power to detect a difference if there really is one. The other thing is we could retain our null. We might get a p-value above our alpha, and we're going to fail to reject, or call it retaining our null. And we could be correct, all is good and true in the world, okay? That null really is true, okay? But we could be wrong. And so in that case, if we retain the null, but it really is false, that's a type 2 error called beta. Notice that beta and power are mathematically related. So in this case, it's just showing you again, but with a particular example that we'll go over in class more. And in this case, you see a diagram, a null probability distribution around the idea that the actual human body temperature is 98.6, that the mean body temperature is 98.6, and that distribution around that represents a null distribution. And the red regions represent where we're going to set our alpha levels, and that represents 0.05 split between the two tails. And of course, it's our error rate. We're going to say that's a rate which we are accepting, that it's rare enough, but we know we could be wrong. Okay. Now, type 2 error rate, on the other hand, we don't get to set that. Okay, why? Well, it depends on a few things. So our beta error can depend on our alpha level, our sample size, and on the actual distribution of the alternative. Well, just like we don't create null sampling distributions, there's no way we can really create alternative sampling distributions. That would be as if we knew the truth, okay? We'll show some sort of theoretical ideas about alternative distributions. But again, these are theoretical. In our null sampling distribution, like with the Salk vaccine, I showed how we made that, right? But of course, we're not going to be making that. We're going to be using theoretical sampling distributions. That's what we're moving towards. Anyway, because of these, we don't get to set type 2 error. There are things we can do to minimize it, though. All right, in this case, I'm showing the beta error based on how much difference I get between a null sampling distribution and this supposed alternative sampling distribution. And in the case here, in the reddish, pinkish, is the alpha error. And all three of these, I'm leaving the alpha at 0.05, split between the two tails. The only thing that's changing here, in addition to my beta error rate, is my power and the difference that I got in my estimate to the null. Okay, so in the upper left, I measured body temperatures, and I got a 0.1 degree difference between body temperature from that sample, representative of an alternative, and its comparison to the null. So the distribution on the left is the null, and the distribution on the right is the alternative. So at the peak, under the null, it's 98.6 mean body temperature, and this one it would be 98.7 for my 0.1 degree difference. Okay, so the gray is my beta error, and the blue is my power. Well, look what happens from 0.1 degree difference to a 0.3 degree difference. Okay, I had a bigger difference between what I got in my sample data to my null, and that has, without changing my alpha, decreased my beta and increased my power. Look what happens with I get 1 degree difference. I didn't change anything else, and again, my beta error has gone way down and my power has gone way up. So the effect size, the difference between I get my sample and the null matters in that beta error. You know, unfortunately, I don't really get to control for that too much. I'm not really sure what that difference is going to be when I go and sample, So there is one thing, though, that I can really control, and that's increasing sample size. If I increase sample size, I can leave my alpha error alone, and it will decrease my type 2 error, and we'll see increase my power. So here's showing that same idea, but in this case, a difference of 0.3 degrees, so that's not changing now. My alpha's not changing now. The only thing that's changing is my sample size. So when I have a sample size of 25, still have pretty high beta error, some power, low power there. Look what happens when I go to 50. I decrease my beta error a lot and increase my power a lot. Look what happens when I go to 1,000. Wow, look at that power to detect a difference if there really is one. And my beta error is very, very low, but I've left my alpha alone. This is an applet where you can go and play around with these things and its effect on beta. You can play around with differences in alpha, and what it does, it will calculate your beta error for you, and it will calculate your power. So you can look at my examples here and go to this and play around with it, where I have a null body temperature of 98.6, and then I sampled and I got 99. Body temperature is my mean, and so 0.4 difference there, and you can see that in the first upper left I kept my alpha at 0.05. It calculated my beta and my power, and in all these cases I kept the sample size the same. I decreased my alpha very low in the upper right. That increased my beta error a lot, and my power went way down. And then you can see in the bottom one, I increased my alpha a whole bunch, which decreased my beta, and my power went really high. But is that meaningful? So go and look at this, because you can really just kind of play with these parameters and see what sample size does, increasing or decreasing your alpha, increasing or decreasing the difference between your means. So I mentioned this statistical power is related to beta. So the same things that reduce beta increase power. Primarily, right, our big one, underline, bold, increase sample sizes. Of course, if we get those bigger differences, yay. Of course, if we increase alpha, which we already saw. And of course, accurate data always matters, right? If you do sloppy measurements, it doesn't matter what you get at the end. So we always want to make sure the variability that we have in our sample data reflects real biological variability and not sloppy measurements. Okay? So we've really gone over all the basics of null hypothesis statistical testing, but there are a few other considerations. Number one, we never prove anything, right? Especially, let's say we get a non-significant result. We aren't proving that a null hypothesis is true or false. So if we say we fail to reject or retain the null, that doesn't mean we're accepting it, okay? We're just saying that we can't exclude that null as a possible outcome. Okay, difference might be detective, but it's not conclusive, and it may not be real if they aren't statistically significant. And so don't think that saying I got a p-value that's high means the null is true. That would be incorrect thinking. The other thing is, of course, don't forget about the possible error in there, and that's the type 2 error. We also have this idea of significant versus important, okay? We're not using the lay meaning of this. In statistics, if we say we get a statistically significant result, that only means that our probability of value associated with our test statistic was below alpha, and meant that we think the difference that we detected, or whatever that test statistic is telling us, did not occur by chance alone. Okay, whether that's biologically important is a whole nother issue, and we have to look at other things, okay? We need to look at the difference between the group, which way it's going, whether that difference is large enough, whether or not it's biologically meaningful. So, we don't want to stop at p-values. We want to look at other things and include them in our conclusions that we reach. Okay, sometimes p-values are not the end-all be-all. Okay, if you have very large sample size between a control and treatment group, let's say, it's going to be, you're going to have a lot of power, and it's going to be fairly easy for you to get a low p-value. Okay, that doesn't mean it's important. Okay, here's the example with the 1% increase in fatal car crashes. It's statistically significant because we have lots of data on car crashes, but the 1% increase, not very big, is it? Are you going to stop driving on full moons? Okay, the other thing is, some important facts may be missed if we get an insignificant p-value, in other words, a high p-value, and if we just stop there and go, well, the null must be true, so I'm not going to do anything else. No, we still want to look at other things. Streptokinase is used as a treatment for stroke victims. In the first studies, they showed that the symptoms from stroke were reduced in the patients treated with streptokinase versus the control. So the means, it did show a reduction in those effects, or in the treatment. But they had small sample sizes, so they didn't have a significant p-value, a low p-value. Did that mean they should stop? No, they looked at those means. They said, hey, it went in the direction we wanted. We needed another follow-up study. And indeed, a larger study was done, and significance was found, and in the same direction. Okay, again, statistically significant finding doesn't mean it's important. More people are scared of spiders than puppies. Oh, really? So we need other things to look at non-significant results to know if we have other pieces of information that indicate that non-significant result has even more meaning for us, that it's real, that some treatment's not effective. And an example here is hormone replacement for post or menopausal women to reduce symptoms. And there was a large study, didn't get a low p-value, so failed to reject the null. So they're saying, well, maybe they looked at the means. Maybe there was a slightly smaller difference in menopausal symptoms for women treated with HRT, but it wasn't significant. Well, in addition to looking at those differences in the direction of the difference, we also have to look at the difference between those groups and a confidence interval around that difference. And if that confidence interval around that difference is very small, we have a little more certainty in what we're seeing, okay, because that means we'd have more precision. And so not only was it not significant, but we're feeling even better that it may not be a good treatment, especially with the potential side effects. So we have confidence intervals that we need to consider, okay? So we do our null hypothesis statistical test. It's going to tell us whether we got a result that is due to chance or no, was a rare event, right? But we also want to look at confidence intervals. Of course, we're going to look at confidence intervals that we create around our mean and reduce those confidence intervals as much as possible. We could also then, as I said previously, look at the confidence interval around the difference we saw in the two samples. These approaches complement each other, and they almost always agree. So we're going to look at several things that we can look at for confidence intervals around the means and their differences from sample to sample. We're going to look at confidence intervals around the difference in, say, a control and treatment group and what that means. As an example, though, let's look at this next slide. In this case, I just kind of want to look at some general approaches to confidence intervals around a difference between two groups and what that can mean, what it can tell us. And this is not looking at p-values at all, okay? Heart attacks. Got a new treatment for heart attacks. You only consider it useful if it reduces heart attack risk from 30% to 25%. So you need a reduction, a mean reduction of at least 5%. Let's look at scenario 1. You get a 10% reduction, so that was your mean, and you get a confidence interval around that mean difference of 7% to 13%. Okay, you're feeling real good here. Not only do you have a point estimate, a mean reduction of 10%, but the confidence interval around that is small and does not go below 5%. So you're feeling good about this treatment, that you have a lot of evidence that it's effective. Scenario 2, you have a good point estimate at 10%, but the confidence interval is wider. And as a matter of fact, it goes below 5%. So the point estimate is in the way you want it, but the confidence intervals, you're thinking more studies, right, to look at this. Scenario 3, even less sort of evidence for you. While you have a high point estimate of 10%, this very wide confidence interval from negative 0.1% to 20%, it overlaps a null value that you would have expected to see here. Think about it. Your null reduction in heart attack for the treatment and the control would be 0%. That confidence interval overlaps 0. So I can't rule out the null as a possible thing. No effect of this treatment, even with that point estimate at 10%. Scenario 2, of course, I have evidence in the exact opposite, that this probably is not effective. Why? My point estimate is lower than 5% at 2%, and my confidence interval is narrow, and it doesn't overlap 5%. So just some misconceptions about hypothesis testing, okay? The probability value is not that the null hypothesis is false. It's the probability of getting a result, a test statistic, extremely, that as extreme or more extreme, given under the null sampling distribution, okay? So the probability that you got some result by chance alone. A low probability indicates a large effect. Not so. Confidence intervals will be more important there. We'll also see another measurement called Cohen's d that we can do to estimate effect sizes. And most importantly, a non-significant outcome means that the null hypothesis is probably true. No, no, no. It just that means it's included in the range of possible outcomes.